problem we're going to look at right now is the lowest common ancestor of a binary tree. And this is number 236 on LeetCode, and it's considered a medium difficulty problem that you might run into in a coding interview. So the question is, if we're given a binary tree, find the lowest common ancestor of two given nodes in the tree. And the definition of the lowest common ancestor is that it's between two nodes, P and Q, such that is the lowest node in your tree that has both P and Q as descendants. And we allow a node to be a descendant of itself, and this is an important distinction to keep in mind. So as we look at this problem statement, there's a couple key pieces of information to think about. First is that this is a binary tree, not a binary search tree. So this may not necessarily have ramifications for this problem, but if you see binary tree, never make the assumption that it's a binary search tree without talking with your interviewer first. So we know that a node can either have 0, 1, or 2 children. Now, we also know that we are given the two nodes to the tree and that they exist in the tree. So this does allow us to optimize later because we don't have to exhaustively search the tree to see if the nodes even exist in the tree. We know they do. So let's go through a couple of examples and that'll help us come up with a solution. So when I'm working with binary trees, I like to throw recursion at it first before I try anything iterative, just because iterative solutions tend to be harder to debug for me, although you might find it to be different for yourself. So taking the image from the actual example, let's look at two different examples we have. We have our tree, and then I'm searching for 5 and 1, and I'm going to be starting at the root node here. So as I'm looking at this, what can I do? I can check my root node to see if it's either P or Q. Now, if my root node happens to be one of the nodes I'm searching for, I can just end the problem, right? Because there is not going to be a common ancestor that is above the root node. So I could just end it there. So that's something to think about as maybe a base case for my recursion. Now, I need to search to the left and to the right. So I'm going to have my base case, and then I'm going to search to the left first. See if I can find on the left-hand part of the tree if one of the nodes I'm looking for exists. If I find it, which in the case I do here with 5, well, I can just stop searching here. The reason why is because if the next node I'm looking for exists somewhere deeper beyond this node, well, there is a little optimization that we can talk about in a second that'll save us a bunch of time. So for now, I'm just going to return the node if I found it. On the right-hand side over here, I'm going to check, and I found my node, I'm going to return it. So after I've found what left and right are for this given node, I need to do a check. Do I have a left and do I have a right? If I have a left and a right, that means that I have found both P and Q to either side of this node. And at this point, this would be the lowest common ancestor, so I would return the current node that I have. But again, this is a very simple example. Let's talk about a harder one, where I'm looking over at 5 and 4. The start of this problem would be very similar to the previous one, where I would go to the left, I'd find my 5, and then I would return it. But then I go to the right. 1 is not what I'm looking for, because I'm looking for 4. I'm going to search to the left of 1. 0 is not what I'm looking for, so I'm going to search to the left and right. Both of these are none. So instead of returning a node, I'm going to return none. Okay? So now I've got none for the left of my 1. I'm going to search to the right. And 8 is not what I'm looking for. I search to the left and right and find none. So I return none back up to 1 here. So I've got none for left, none for right. I'm going to return none here. So now what I have at 3 is 5 for left and none for right. What does this mean? Well, since we know that P and Q exist inside of this tree, and one half of my tree doesn't have any of the nodes, and then my other one, I've only found one of them. That means that my other node must exist somewhere deeper in this left-hand side of the tree. So therefore, the one node that I did find would actually be the parent node for both of them. So let's code this. It'll make a lot of sense when we work this out. So we're going to be working with recursion. We need to have some kind of base case. So if we don't have a root node, we're going to want to return none, or itself in that case, because root is equal to none. So if not root. But also remember, if I find P or I find Q, I also want to return it. So just to make the code a little bit cleaner, I can go if not root, or root is equal to P or root is equal to Q, I'm going to return root. In the case where I don't have anything in root, I will be returning none. Otherwise, I will be returning one of the elements. And that's exactly what happened here, where I would be returning none, and I would be returning an element for 5. Okay, so that's my base case. Now I need to search to the left and to the right because I don't want to return the current node I'm looking at until I know if one of the nodes that we're looking for is below it. So left is equal to self dot lowest common ancestor, spell it right, ancestor, root dot left, and then I'm going to pass P and Q to it as well. And then right is equal to self dot lowest common ancestor, and it's going to be root dot right Q. Okay. So now I have left and right, and let's go back to what we were talking about before. If I have both a left and a right node, then I know that the current node I'm staring at is a ancestor for both of the nodes P and Q. So if left and right, return root. In this case, because we already found both of them, so what we're returning now is the lowest common ancestor. Now, if I only have something to the left or I only have something to the right, what does that mean? Well, when I finally reach my root node, that means that one of the nodes, either P or Q, exists past the other one that we did find. So therefore, we're going to return the one that we did find as the parent for both of them. So return left or right. So let's run this. You'll notice that we pass our first 3 test cases, so let's submit this. And we've solved the problem. So let's go back to this problem, this diagram's over here, and think about the complexity. What's the time complexity? Well, think about an example like this where I have 1, 2, 3, 4, 5, and I want to find 1 and I want to find 5. In this case, I would have to traverse the entire tree. I would have to touch every single node. So at a minimum, my worst case is going to be big O of n. Okay. What's the space complexity? Well, again, since we're calling recursion, we're going to be putting stuff onto the stack as function calls. I would again have n function calls, so it would be big O of n as well for the space. You could also think of this as the height of the tree. Regardless, either answer should work for an interview. Thank you.